All right, let's talk about real-world data. The messy stuff, the data that doesn't follow the textbook examples. Today, we're diving into a tool that's built for exactly that kind of challenge. It's a statistical powerhouse called the Mann-Whitney U-test.
So, picture this. You've done all the hard work, you've got your data, and you're ready to find some answers. But then, you hit a wall. See, a lot of the classic tests, think of the t-test, they have this one big rule. Your data needs to look like a perfect bell curve. But let's be honest, how often does real data look perfect? So what do you do when your data isn't normal?
Well, you definitely don't give up on your data. No way. You just need a different kind of tool for the job. You need something more flexible, something built for the real world. And that's where non-parametric tools come in. They're designed from the ground up to work with data exactly as it is. No assumptions needed about its shape.
So here's how we're going to break this down. First, we'll get a solid handle on what this power tool is. Then, we'll do a head-to-head comparison with the t-test so you know exactly when to use which one. After that, we'll cover the rules of engagement, the must-knows before you start. We'll walk through the test in action with a real example. And finally, we'll wrap it up with your key takeaways.
All right, let's get right into it. The non-parametric power tool. So what exactly is the Mann-Whitney U-test?
So here's the formal definition. It's a non-parametric test, and that phrase, non-parametric, that's the magic word. That's its superpower. It means the test doesn't demand your data fit into a neat little box. It couldn't care less if your data is skewed or lopsided. Its whole purpose is to look at two independent groups and ask a simple, powerful question. Does one of these groups tend to have bigger values than the other?
Now, a quick heads up. You're going to see this test under a few different aliases. Mann-Whitney Wilcoxon, Wilcoxon ranks sum test. Don't let it confuse you. It's all the same thing. The easiest way to think about it, it's your number one alternative to the independent t-test. It's what you grab when a t-test just won't work.
Okay, so this brings us to a really crucial point, choosing the right tool. Let's put the t-test and the Mann-Whitney U side by side. Honestly, knowing the difference here is what makes you a smarter, more effective analyst.
This table really lays it all out. A t-test focuses on one thing, the average, the mean. It's asking, is the average height of Team A different from Team B? Simple. But the Mann-Whitney U, it looks at the whole picture, the entire distribution of ranks. It's like lining up every player from both teams and asking, in general, does one team's players just tend to be taller than the other team's players? It's a much broader question.
So how on earth does it do that? Well, it uses a really clever and actually pretty simple idea. It ranks everything. Forget the actual values for a second. Imagine you've got two groups of marathon runners. Instead of comparing their average finish times, you just line up everyone from both groups based on who finished first, second, third, and so on. That's the rank. Then you just look to see if, say, the runners from Team A are all clustered near the front of the line. That's exactly what this test does with your data.
Okay, before we just start using this tool everywhere, we need to talk about the rules of engagement. Think of this as the pre-flight checklist. There are just a few key assumptions you have to meet to make sure your results are legit.
And the good news is, these rules are pretty straightforward. First, your samples have to be random. Makes sense, right? You need them to represent the bigger picture. Second, everything has to be independent. That just means one data point can't affect another, and you can't have the same person or thing in both of your groups. And finally, the data needs to be at least ordinal, which is just a fancy way of saying you have to be able to rank it, from lowest to highest. And honestly, most data fits that bill.
All right, enough with the theory. Let's get our hands dirty. We're going to see this test in action with a real case study, step by step. So here's the setup. We have a researcher who wants to know if there's a difference in the biomass, basically the total weight, of male and female juniper trees. We've got two separate groups, male and female. The data probably isn't perfectly normal. This is a textbook case for the Mann-Whitney U-test. So like any good test, we start with our hypotheses. The null hypothesis, H0, is our baseline assumption that there's no difference. The distribution of biomass is exactly the same for both male and female trees. The alternative hypothesis is just that they're different. And notice that wording. We're not saying the average is different, we're saying the entire distribution is different. That's a key distinction. And here is where the magic happens. The researcher took all 12 trees, ignored which group they belonged to for a second, and just ranked their biomass from smallest to largest, 1 to 12. Then they put them back in their original groups. And just look at this table. You can already see something happening, can't you? The ranks for the female trees, 9, 10, 11, 12, they're all piled up at the high end. And the sum of those ranks makes it super clear. 23 for the male trees, and a whopping 55 for the female trees. Okay, so how do we turn that observation into a hard number? With these formulas. Now don't let them scare you, they're actually pretty simple. The n's are just our sample sizes. We have 6 male trees and 6 female trees. And the r's, that's just the sum of the ranks we just saw, 23 and 55. We're just going to plug those numbers in. So we plug everything in. For the first group, U1, the math works out to 34. For the second group, U2, it comes out to 2. Simple as that. Now we have our two U values, 34 and 2.
And here's the next step, and it's an easy one. The actual test statistic, the final number we care about, is just the smaller of those two values. So between 34 and 2, our final U statistic is 2.
So we have our number 2. But so what? Is 2 a big deal? To figure that out, we have to compare it against something called a critical value. You can just look this up in a table. Think of it as the cutoff point, the line in the sand. For our specific experiment, that critical value is 5. So the final comparison is our number, 2, versus the cutoff, 5. Okay, hold on. This is the part that feels a little weird, and it trips a lot of people up. In most statistical tests you've probably seen, you want a big number to get a significant result. But here, our calculated value, 2, is smaller than the critical value, 5. And that means we found a significant difference. So what's going on? Why is smaller better here?
Here's the logic, and it's actually really elegant. A U value of 0 would mean the two groups are perfectly separated, like one group has ranks 1 through 6 and the other has 7 through 12. There's no overlap at all. So the smaller your U value is, the closer you are to that perfect separation. A small number like 2 means there is very little overlap between the group's ranks, far less than you'd expect from random chance. So that small U value is our signal. It's telling us that yes, there is a significant difference. The female trees really do tend to have a higher biomass.
Okay, time to wrap this up. Let's boil it all down to your key takeaways. This is the consultant's briefing. If you remember nothing else, remember this.
Okay, 3 things. Number 1, the Mann-Whitney U is your go-to move when you're comparing two independent groups, but your data isn't playing by the normal distribution rules. Number 2, it's all about ranks, not means. You're asking if one group tends to have higher values, not if their averages are different. And number 3, and this is the big one, remember the smaller is significant rule. You're looking for a calculated U that is less than the critical value. That's your green light.
So I'll leave you with this question. Think about your own work, your own data. What projects have you put aside, or what questions have you been afraid to ask because the data just wasn't perfect? Now that you have this tool in your back pocket, what can you go back and re-examine with fresh eyes?